Okay, so then we'll move now to the last part of the lesson, eigenvalues and eigenvectors of 2 by 2 and 3 by 3 matrices. Okay, so an eigenvector of a matrix A is a non-zero column vector X. Can you see? An eigenvector of a matrix A is a non-zero column vector X which satisfies the equation Ax equals lambda X, where lambda is a scalar. Okay, so these are main equations that we use in this lesson. Ax equals lambda X. Write down the value of the scalar lambda is the eigenvalue of the matrix corresponding to the eigenvector X. Okay, so they say here the word eigen is German and means particular or special. Okay, eigenvectors are also known as characteristic or latent vectors. Okay, so then they say here the magnitude of the eigenvector may be changed by linear transformation represented by the matrix where the direction of the eigenvector is unchanged or invariant. The eigenvalue can be interpreted as the magnification factor of the eigenvector under the transformation. So basically, if we go into the important thing here, look at this. If X is an eigenvector of the matrix here, then by definition, Ax equals lambda X equals lambda Ix. You know, write down these things. These are the important things. When you rearrange, we can get Ax minus lambda Ix equals to 0. As by definition, X is non-zero, the matrix A minus lambda is single and has determinant 0. That is, determinant A minus lambda is 0. Write down. So these are the main equations that we are going to use in this particular part. Okay, determinant A minus lambda equals 0. The equation determinant A minus lambda equals 0 is called the characteristic equation of A. Okay, so have a note of it. You must know all these, you must be able to use this. So mainly the main equation, there are two main equations we use here. Ax equals lambda X is the first one. And the other one is determinant A minus lambda I equals 0. So these are the two main things that we use in this part. Okay, the next part, a normalized vector is a vector of unit magnitude. Magnitude is 1, okay? In 3 dimensions, you normalize the vector ABC by dividing each element by the magnitude of the vector, which is root A square plus B square plus C square. Look at this. So basically, what we do is here is by a normalized vector, you take any vector. Say, for example, you have vector 2, 3, 5. How do you get the normalized vector? To get the normalized vector, what we do is we take the magnitude of this vector and divide each and every element by the magnitude of the vector. Now, how much is the magnitude of this vector? 2 square plus 3 square plus 5 square root. How much is it? 2 square plus 3 square plus 5 square root. How much is it? Root 30. Can you all please type again? 2 square plus 3 square plus 5 square. So it's going to be, how do you know what's the normalized vector? 2 over root 38. 3 over root 38. The next one, 5 over root 38. Can you see this is called normalizing a vector? So when you normalize a vector, what happens is we create a vector that has magnitude of unit 1. Okay, so before we go into so we will be doing this normalized eigenvectors at the end. Right now, what we will do is we will learn how to find eigenvalues and how to find the corresponding eigenvectors. Okay, so let me show you how it's done. We will directly do it from the question. Okay. Okay, so let's start from the exercise 6 question number 1. Okay, so we'll come to exercise 6 question number 1 and we will learn exactly how to find the eigenvalues and the corresponding eigenvectors. Okay, this is how we do it. So we'll start first with the 2 by 2 matrices. Okay, and then after you are comfortable with 2 by 2 matrices, we will apply the procedure to 3 by 3. Okay. Now thing is this, we'll take the first matrix and name it as A. Now what are you supposed to do? You're supposed to find the eigenvalues. So how are you going to find the eigenvalues? What's the main equation in this lesson? The main equation, there are two main equations. The first one is determinant A minus lambda is equal to 0. What's the second equation? Ax equals lambda x. These are the two equations we are going to use in this lesson. Ax equals lambda x. Are you with me? So determinant A minus lambda equals 0 is one equation. Ax equals lambda x is the other one. So what you do here is first shall we get A minus lambda I. How do you get A minus lambda I? What do you mean A minus lambda I? A is 2, 1, 4, 5, right? Minus lambda is a constant, the eigenvalue. And who is I? I is 1, 0, 0, 1. Can you subtract these two matrices? What do you get? 2 minus lambda into 1, which means the first element is 2 minus lambda. Next one, 4 minus lambda into 0, which is 4. The next one, 1 minus lambda into 0, which is 1. Last one, 5 minus lambda into 1 is 5 minus lambda. Are you with me? This is A minus lambda. Now, what am I supposed to do? I need to find the determinant of A minus lambda. How do you find the determinant of a 2 by 2 matrix? Determinant of a 2 by 2 matrix is we multiply along the main diagonal, right? 2 minus lambda times 5 minus lambda, subtracting with 1 times 4 is 4. Okay, and then what do? We make determinant A minus lambda I equal to what? 0. Let's solve this equation. Can you open? You get a quadratic equation. 2 times 5, 10. Minus 2 lambda. Minus 5 lambda. Minus lambda minus lambda. Plus lambda square minus 4 equals 0. Rearrange the equation. Lambda square minus 7 lambda. 10 minus 4 is 6 equals 0. Can you all factorize this? How much is it? Lambda minus 6, lambda minus 6. So we get lambda equals 6 or lambda equals 1. So what are these lambda values? These lambda values are what we call as eigenvalues. The lambda values are what we call as eigenvalues. Okay, and then what we do is we use the lambda values and can calculate the eigenvectors. Okay. So how do we get the eigenvectors? Finding corresponding eigenvectors. Okay, now look at the way I used to get the corresponding eigenvectors. Did you understand the technique I used to get the eigenvalues? Okay, to find corresponding eigenvectors, first what you do is take one lambda value. So for example, I'll first take lambda is 1. So we'll take lambda equal 1 and apply them. What's the next main equation? I told you there are two main equations. Determinant A minus lambda equals 0. Who is the other equation? Ax equals lambda x. Let's work with this. Ax equals lambda x. And they tell you here x is what? X is the eigenvector. Eigenvector means now you know you are working with a 2 by 2 matrix, right? So an eigenvector is like a column vector. A column vector now in this case, because you are working with a 2 by 2 matrix, your column vector will have how many elements? Your column vector will have only 2 elements. A is who is A? 2, 1, 4, 5. And your x is your eigenvector. X is your eigenvector. And eigenvector, since this is a 2 by 2 matrix you are multiplying, it will only have 2 elements. Are you with me? Lambda is 1. Look at this. When we are working with 3 by 3 matrices, your eigenvector will have 3 elements. The column vector. Since it's 2 by 2, your eigenvector will have only 2 elements. Can you all solve this? What do we get here? 2x plus 4y is the first element. Next one, 1x plus 5y. Do you agree with me? Equal 1x, 1y. So shall we make two equations here? Let's make two equations here. What do we get? 2x plus 4y equals x. Basically, we get x plus 4y equals 0, right? Can you see? And the other equation? X plus 5y equals y, which is again what? Basically, I get x equal minus 4y from both. So actually, what it means here is that your eigenvector is following this rule. Eigenvector can be any point that falls on this particular line. This is actually what we call as an invariant line. So you can see this is the straight line that you get from the that you get by the that you get from the eigenvector, isn't it? So the eigenvector, the xy value in the eigenvector can be any point that lies on this particular line. So you can take any point on it. Take what? Normally what we do is we take the simplest multiple. Take the lowest multiple. What's the lowest multiple we can take? Without fractions, try to get a good value. Yeah, so what's the eigenvector? Yeah. What do you use for y? What do you use? And when you use what for y, you can get what for x. You can use basically any multiple is correct. So tell me the least value. I can use the smallest. Maybe we could go with y equal 1. When y is 1, x becomes -4. It could be anything. You can, I mean, basically any multiple of -4, 1 is correct. So even if you write your eigenvector when y is 2, x is -8, that's also correct. But we normally prefer to keep it in what? Keep it in the simplest form. Okay, so if you say x is 1, then y becomes -1/4. So it's still a multiple. If x is 1, y is -1/4, right? So this multiple, if you multiply both up and down by -4, you again get this. So basically any point that lies on x minus 4y is can be used for the eigenvector. Are you with me? Okay, can you all try to find the eigenvector for lambda equals 6? Get me the corresponding eigenvector for lambda equals 6. Again, the eigenvector is xy. Lambda is now 6. Get me the eigenvector, get me the xy value. So when you open this, you get 2x plus 4y, and here you get 1x plus 5y equals to 6x, 6y. So when you take the two equations, I think you can see 2x plus 4y equals 6x, which gives you 4y equals 4x, which gives you y equal x, right? I think you would get the exact same thing even from the other side. Am I correct to say that? 5y equals 5x, which is y equal x. X plus 5y equals 6y. 6y. And then we get x equals 6y minus 5y. X equal y. So then what's the lowest multiple we could get for the eigenvector? Yeah, so if x becomes 1, y becomes 1. That's the lowest multiple we can take. So take the lowest multiple. Is this clear? Yeah, this is it. So this is how we find how do we find eigenvectors once again? Remind me, we find eigenvectors by getting the determinant of the A minus lambda I matrix. And then using those eigenvectors, we use Ax equals lambda x and calculate the corresponding eigenvector. Is this clear? So this is it. This is the way we find eigenvalues and eigenvectors. It's quite simple. Shall we do one more in practice? Yeah, let's try to find question number 2. Question number 2. Okay, question number 2, they have given you A is equal to 3 minus 2, 4, 9. So did you get A minus lambda I? A minus lambda, shall I write it directly? It's 3 minus lambda, 4 minus 2 and 9 minus lambda, right? Directly. Determinant of A minus lambda I will be 3 minus lambda into 9 minus lambda. Minus 2 into 4 is -8. Are you with me? And we make it equal to 0. So open the bracket, 12 minus 3 lambda minus 9 lambda plus lambda square minus is plus 8. Do you agree? This is the equation, lambda square minus 12 lambda plus 20. Sorry, 3 times 9 is 27. 27 plus 8 is 35. What are the two factors? Which means we get lambda equals to 7 or lambda equal to 5 if we get the eigenvalues. Next, they say find the coordinate equations of the two lines passing through the origin which are Okay, so as I was saying earlier, okay, so when we were doing question number 1, when lambda equal 1 and lambda equal 6, did you notice that we actually got two straight line equations and that we use those straight line equations to find the eigenvector? So these are what we call as the invariant lines under T, which means when you perform the T translation, when you perform the T transformation, any point who is lying on this line, they will not move. I mean, they will move on top of that line. They will not move anywhere else. A point who is on this line will move to another point on top of that line. Okay, so the line x, any point on the line x minus 4y will be invariant under the transformation T. Okay, that's what it means. Now in here also they say find Cartesian equation of two lines passing through the origin which are invariant under T. How do we find it? What do we do? Again, we use Ax equals lambda x. So we'll go with lambda equals 5 and go Ax equals lambda x. What do we get here? A is 3 minus 2, 4, 9. X is xy, lambda is 5 times is xy, right? What do we get then? 3x plus 4y. Here I get minus 2x plus 9y. Are you with me? Equals 5x, 5y. Can I know the equation? 3x plus 4y equals 5x. And I get here 4y equals 2x. And I get y equal half x. Or x equal to y. X equals to y. And I think if you do it from the other equation as well, I believe you get the same thing, right? So 1 is enough. Okay, so we get here 9y minus 5y is 4y equal 2x, and I get y equal half x again. So basically this is one invariant line. How do I get the other invariant line? We go with the other lambda value. So when lambda is 7, ax equals lambda x. A is 3 minus 2, 4, 9. X is 7 times xy. 3x plus 4y. This is minus 2x plus 9y. X plus 4y equals 7x, and I get here what? 4y equals 4x, right? Which means y equals, so this is the other invariant line. Even if you solve the other equation over here, you would still get y equals x. So the two invariant lines under the transformation T is y equal x and y equal half x. So any points lying on the top of those two lines are invariant under the transformation T. That's really important. Okay. Do you understand? So this is why we do these eigenvectors and the eigenvalues are found so that you can find points which are invariant to the given transformation. Invariant means what? That they are if they are invariant, they don't move, or basically you could say they map to points on that same line, which means at the end of the day the line is still the same. Now you saw in the previous exercise when we were doing, you saw the lines were transformed to completely new lines, right? When we transform the object line, the image line was something totally new. But the thing here is these two lines are invariant. So if you try to move this as the object line, the image line will be exactly the same. So they are invariant. They will not change. Okay? Okay, is this clear?